Hey Sparkies, today's video is going to be about inductance and inductive reactance. I'm also going to do a video to show you time constants for inductive circuits, but now I want to take a moment to talk about inductance and how it's affecting an AC circuit. So there are factors that affect inductance, okay? Factors that affect inductance. And they can be demonstrated with a formula. And the formula is this: L equals number of turns squared permeability times area, all divided by linkage path. So pretty much every variable we're going to talk about in second period is going to have some type of a formula that has concepts that are related simply to the way that they are written in a formula mathematically, okay? So I want to say, okay, so L is inductance, and the unit of measurement for inductance is the Henry's. So the N, in this case, is squared, and that is the number of turns, okay? So a coil or inductor is many turns of a fine wire. That can be on some type of a core, can be air, can be iron, lots of different types. So number of turns. The symbol here is permeability, and that's the ability for the core to conduct lines of flux or support lines of flux. So that's permeability, that's the symbol. Permeability. Oh my God, that's spelled wrong, but permeability. There it is. And then A, that is your area, and that is the area of the core. Okay? So all of these components are considered directly proportional to inductance. Meaning if I were to increase any of these variables, the inductance would react proportionally, the same. So if I were to increase the number of turns by double, I would essentially double the amount of inductance in the circuit. If I were to decrease the permeability of my core, let's say replace my iron core with an air core, that would decrease the permeability. You would see that have the same effect on the inductance. If this were to go down, then the inductance would go down, okay? Area is also directly proportional to inductance. So if I had an iron core that had a specific area and I doubled it, you would see the inductance would proportionally do the same and double in value, okay? So everything, where is my eraser? Everything on the top portion of the formula is directly proportional to inductance. That leads me into the next part. Oh, there it is. The bottom is your linkage path, and that is indirectly proportional to the amount of inductance that's created in a circuit containing a coil. So that's, I want you to think about when you're energizing a contactor or a coil, you see that armature snap in. That pathway is the linkage path that I'm talking about. So if the space between your armature is increased, you're going to have the reverse effect. So increase in linkage path is going to lower my inductance. If I were to decrease the space between those components, I would have the inverse or the opposite effect. It would increase. So that's quite handy to know. If you recognize the formula, L equals number of turns times permeability times area divided by linkage path, you can answer a lot of questions in regards to how an inductor is going to react in a circuit. Okay, so if I increase the number of turns, inductance goes up. If I increase the permeability, inductance goes up. If I increase the area, inductance goes up. And if I increase the linkage path, my inductance goes down. So it's important that you understand and recognize this formula and are able to manipulate it. Okay? So I want to come back to talking about how an inductor affects the amount of current flowing in a circuit. So my previous AC principles video, I showed you how a coil opposes a changing current, not like its counterpart of resistance opposing straight on current flow. It opposes change. We facilitated that change with a switch, opening and closing of a switch. I also want you to be aware that because we are using AC generated, we're having our frequency play a part of a change as well. So we're basically having 60 cycles per second occurring, and that's also facilitating some change and counter EMF. Okay, so I want to talk to you about expanding or collapsing magnetic field. Okay, so here I have my current flow. Okay, and that's going into the page. Okay, so current is going into the page and it's creating magnetic field around this current or this flow that's going. So if I'm going into the page, left hand rule, okay, so that means my magnetic field is being set up in this direction. Okay, so when you have current flowing in a conductor, you have a magnetic field that's surrounding that conductor. So what's going to happen if that conductor is connected into a coil is that I'm going to create a counter EMF. Okay, and it's all going to depend, my inductor is going to react depending on if it's expanding or collapsing. So let's say I have the switch closing, therefore I'm facilitating an expanding magnetic field. What's my counter EMF going to do? Okay, so that's what these circles are representing, the counter EMF. Okay, so right now I have an expanding magnetic field. Okay, so I've closed the switch, current wants to rise. My counter EMF is going to do what? My counter EMF is going to produce a magnetic field that's opposing my line current. Okay, so basically my counter EMF is now going to oppose it by creating current flow going in the opposite direction and then creating a magnetic field around that counter EMF that's going to oppose that original magnetic field. Again, you're using your left hand, thumb points in the direction of current flow, and then my fingers are representing the magnetic field that's produced. So they're going this way. So you can see here now that my counter EMF is slowing the current from rising to maximum by creating a counter-magnetic or a counter EMF that has a magnetic field going in the opposite direction. That is how an inductor reacts in an AC circuit and an expanding magnetic field. Okay, so now let's look at a collapsing magnetic field. Okay. So if I have, again, my supply, current is going into the page, left-hand rule, fingers are demonstrating the magnetic field set up around it. Okay, so again, they're going in this way, but I'm demonstrating collapsing magnetic field. Okay, so that's the change being facilitated. What is my counter EMF in my coil going to do? Okay, so when my field was expanding, the counter EMF created a magnetic field that was opposing the magnetic field that was set up in our main line. So now a collapsing magnetic field is going to want to keep that current from dropping to minimum immediately by producing a counter EMF that's going to aid the collapse. Okay, so it's going to create a magnetic field that goes in the same direction as our incoming current. Okay, so again, left hand rule, thumb goes into the page, current flow creates a magnetic field around it that's going in the same direction. Okay, that counter EMF is going to keep our current from going immediately to minimum. Okay, so just wanted to give you a little bit of information in regards to an expanding and collapsing magnetic field. Next, I want to talk to you about is a coil that has inductance reacts to changing current in an AC circuit, and that reaction is known as inductive reactance, and it's created due to this counter EMF. That is the variable of impedance that's affecting our overall current flow. Okay? The formula for inductive reactance is XL equals 2 pi FL. Okay, so XL is inductive reactance, and that's measured in ohms. 2 and pi are constant. Okay, pi is your 3.14. F is your frequency, and that's measured in hertz. Typically you're using 60 hertz, but be aware that they can change that. And then L is your inductance in henries. Okay. Henri. All right. So I want you to recognize that 2 pi FL are all directly proportional with inductive reactance, okay? Meaning that if I had a coil and I doubled the amount of turns on my coil, how would that affect my XL? Well, let's look at that for a second. Okay, let's go back to L equals number of turns times permeability times area divided by linkage path. Well, if I increase my number of turns, my inductance goes up. If my inductance goes up, what's going to happen to my inductive reactance? Direct proportion. It's going to go up, okay? So what about frequency? Let's say I decrease my frequency. What's going to happen to my inductive reactance? Again, everything mathematically here is a direct proportion. If frequency was half, then my inductive reactance would be halved, okay? So again, just by knowing the formula, you're going to be able to answer lots of questions in regards to inductive reactance, okay? So 2 pi FL, let's look at that in terms of a circuit. So let's say I have a coil that has, so a coil has 0.6 henries. The frequency of the circuit is 60 hertz. What is the XL or inductive reactance in the circuit? Okay, XL equals 2 times pi times frequency, 60 hertz times 0.6 henries. And that gives me an inductive reactance of 226.2 ohms. Okay, so if I had a purely inductive circuit, okay, purely inductive circuit, coil, 120 volts, okay, our XL equals 226.2 ohms. A purely inductive circuit means that there's no variables of resistance contained. It means that there is no capacitance or capacitive reactance. So that means in my AC circuit, I equals E over Z, Z for impedance. Because it's purely inductive, I can replace my Z with my XL in this case, okay? So 120 volts divided by 226.2 ohms, that gives me a current of 120 divided by 226.2 equals 0.53 amps. Okay, so be comfortable with manipulating, transposing your formulas, and recognizing that you can answer a lot of questions in regards to its proportion mathematically. Okay, the next video will be on time constants. Thank you.